Okay, let's talk about the Williamson synthesis. If you recall from our acid-base chemistry discussion, you may remember that alcohols have pK of about 16, and what that means is that if you treat alcohols with the conjugate bases of certain molecules, like for instance dihydrogen, if you take the conjugate base of dihydrogen, now you're dealing with hydride, in this case sodium hydride. This is a pretty strong base. Strong enough that it can actually fully deprotonate the alcohols themselves. And so what this ends up doing is creating alkoxides, the conjugate base of alcohols, right? In the process, you produce hydrogen gas that exits out of the flask, and the sodium, which is just there to balance the charge. Now, I know that I'm drawing it here as having a bond, but technically this is ionic, so this should be sodium plus 1 and H minus, with the H having the 2 electrons, right? So this is really an ionic bond. I happen to draw it this way just for convenience, but it's something to keep in mind. The sodium is going to go wherever negative charge develops, right? Currently, in the reactant side, the negative charge is on the hydride, but on the product side, the negative charge will be on the alkoxide side. So the sodium is going to go wherever that goes. And notice here that for the mechanism, I'm only accounting for the electrons that are technically bound to the hydride attacking the hydrogen of the alcohol. The electrons of that OH bond get pushed back to the oxygen itself, thus creating your sodium alkoxide and your hydrogen gas as products. Now, even though the alkoxide is a weaker base than hydride, it is still considered a strong base. And the reason why you have to kind of keep that in mind is because when you're trying to synthesize an ether using an alkoxide, which is technically this Williamson synthesis, you're going to be doing and relying on the idea that this is going to go via an SN2 reaction. But if your carbon is too substituted, you will not be able to do that SN2 reaction. And unfortunately, SN1 reactions are not really available with alkoxides because the fact that alkoxides have strong bases negates the SN1 reaction, which will require, at the very, in the worst case scenario, moderate neutral conditions, but ideally acidic conditions. So this has to go be an SN2 reaction. There's really no choice there. So when the alkoxide attacks that electrophilic carbon and the leaving group takes off, that's how you end up forming your ether functionality. But in practical purposes, this is really only going to work if your carbon diverse the leaving group is methyl or primary. If you got a secondary carbon, you're probably going to start doing eliminations. And needless to say, if you have a tertiary alkyl halide, you'll end up undergoing eliminations for sure, right? So yeah, secondaries is really not going to work out too well. Not to say that you will not get some SN2 product, you probably will, but your yield is going to be terrible, right? So you want to kind of avoid that and just keep it to methyl and primary alkyl halides when it comes down to this. All right, so let me give you an example of this issue. Let's say that you are trying to synthesize the following ether, and you want to approach it using the Williamson synthesis. Well, what you have to first determine is what kind of carbons are directly bound to the oxygen of that very ether. And if you look here on the right side, this carbon is actually primary, whereas the carbon right here is secondary. So what this is telling you is that out of the two options, you want the carbon that is primary to become your alkyl halide, and then the secondary carbon to contain the oxygen from the very beginning. In other words, you want what we've highlighted here in red to be your alkoxide. And initially you're going to start with an alcohol, which you convert to alkoxide, but this will be what contains the oxygen the entire time. And then the next part, right, the primary carbon plus the rest of the stuff is going to be your alkyl halide. So in essence, as far as your synthesis goes, you start with that alcohol, the cyclopentanol. You treat this with sodium hydride, which is a stronger base than alcohol. Oh, and by the way, sodium hydride is just one out of the many bases that you could use to deprotonate alcohols. As long as the base that you use is a stronger base than alkoxide, this deprotonation will happen to completion. So it could be deprotonated amine, it could be an alkalide type of reagent, deprotonated alkyne, any of those things which are technically stronger than alcohols could serve to deprotonate this. So it doesn't have to be necessarily hydride itself, but hydride can do the job. So it will deprotonate, will attack the proton of the alcohol, the electrons will get kicked out back to the oxygen, and this will generate your alkoxide. And once more, sodium now goes with the alkoxide, which is negatively charged. Now this base has to react with the alkyl halide. In this case, I chose bromide to be the leaving group. It could have been chloride as well. The only one you do not want to choose is fluoride. Fluoride is actually a terrible leaving group, and in some cases, not really much of a leaving group because it's really formed a strong bond between it and carbon. So as long as you stick to chloride, bromide, iodide, those are good leaving groups. With iodide being the best, but a little bit less practical to deal with due to the fact that it can create radicals relatively easily. Okay, so here with the bromide, we attack. We have the oxide electrons. Remember, once again, this is sodium plus and this is O minus with 3 lone pairs. So this is one of the lone pairs, technically speaking. That attacks that electrophilic carbon, the bromide takes off, and the bromide automatically combines with the sodium plus to precipitate out the sodium bromide. And in the process, you generate your desired ether. Okay, so that's the way in which you go synthesizing your ethers via the Williamson synthesis. In the next video, I'm going to show you how you can form epoxides and how you can utilize epoxides to make further ethers. So I'll see you in the next video.